Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. We will continue from where we left in the previous turn, primarily looking into the doping and concentration variation because of freeze out. Out of which, let me come to an important sort of parameter which refers to as dwell time, right? Dwell time, it's basically just like in English literature or English language. Dwell is basically how much time one stays at a particular position. So, basically if you look at the definition, dwell time refers to the average time a charge carrier, electron or a hole will remain trapped in a localized energy state before it escapes, right. So, it is something like this, like you have a classroom, right, and in the classroom there are empty chairs available. Now, somebody comes from the outside, it sits in the fixed chair in that room, right, and then suddenly because of some reason leaves the room again, right, or leaves that space where it was occupying that localized energy position. And if you statistically take 100 such carriers or 1000 such carriers or million such carriers over a period of time and average it out, then the average time which a carrier spends on these localized places or localized energy states is referred to as dwell time. Now, if you understand it very clearly, these localized sort of energy states, also referred to as traps, have got low energy. So, these are basically stable energy states available, right. So, typically the traps work is that these carriers always like to occupy those traps which has got the lowest energy, right, and how much time it occupies depends upon the temperature as well as external electric fields available to us. Now, if you plot dwell time versus temperature, which is shown on the right hand side here, then qualitatively even quantitatively, if you see that at high temperature, even at moderate temperatures, the dwell time becomes very small, the average dwell time becomes very small. So, the order of 10 to the power 5 to 10 to the power 10, right, seconds. Whereas, when the temperature goes down to even 10 Kelvin, you see there is a substantial rise in the dwell time to a large value of 10 to the power 20 to 10 to the power 25. And this rise is primarily because since the temperature has gone to such a low value that the thermal energies are so low that the electrons do not leave their state and go out of that state, right. That is the reason here, and therefore, at low temperatures, you see at low temperatures the carriers remains trapped for a longer time, right, because there is not thermal energy available. However, at higher temperatures the carriers escape faster because of the large amount of thermal energy required. Also, if I assume that the external electric fields are also large, it will be able to pull the electrons with them at a very fast pace. Now, it is very important when you do a cryogenic electronics that this dwell time is of very importance, because it actually tells you sort of how the freeze out effects get affected, what is the overall reliability of the device at different temperature is given by the dwell time. So, dwell time is one factor which, just for the knowledge sake, also it is important to understand the freeze out effect. Now, as I discussed with you, as the temperature increases, the dwell time increases rapidly, right, and typically the value is around 25 Kelvin. So, around this place the dwell time is around 1 second, right. And 1 second, please understand, is very large in terms of electronics, because it is typically a large quantity which you are referring to. At t equals to 10 Kelvin, dwell time for holes is 10 to the power 5 seconds, which is effectively 10 million years, right. Is it okay? Which means that at t equals to 10 Kelvin, an electron can stay for infinitely long duration of time without, if you do not change the temperature, of course, and there is no external field which drags it. And this is the average time that the trapped holes remains in the level, right. And therefore, you should understand that at cryogenics, be it electrons or holes, they almost behave like a frozen particle. You cannot remove that particle from the trap. Therefore, it also adds it to the freeze out effect, that there are no available carriers at low temperature to contribute to the flow of charge carriers, right, and that is what is known as at low temperature you have a problem. Now, typically if you apply an external bias, right, an external electric field, then this external electric field will sweep out the trap. So, it is not only important that the temperature rises and therefore it releases electron from the traps, but since it is a low energy state, if there is no sufficient external electric field, these electrons will never be dragged or drifted away from its localized position, and then they will again fall back to the low energy state, which is the trap itself. So the dwell time is very small, right, at relatively higher temperature, but you need to also have an external electric field in order to sweep out the free charge carriers from the region, right. This is quite important. So two things you need to ensure, that you do have external electric field available and you do have small variation in fluctuation. Now what happens, I will give you from cryogenic point of view, that there might be certain fluctuations. It is very difficult to maintain 10 Kelvin or 4.2 Kelvin at a particular place. There might be certain fluctuations which happen, and these fluctuations are such that these fluctuations tend to sort of, temperature fluctuations tend to make the probability of dwell time go slightly lower, and therefore they will leave that localized energy state and come out, right. So that is the reason you need to be equally effective, that there might be thermal fluctuations taking place. These fluctuations are not very heavy, but even if you go back to that slide which I was showing you earlier, even if there is a 10 Kelvin fluctuation, you see if this is my 10 Kelvin here and this is the 20 Kelvin here, you see your dwell time has actually gone down by about 10 to 12 orders, right, and that is quite critical in terms of localized states. Now the effective short dwell time, when you have temperature the order of few kelvins, then the trapped charge carriers escape the thermal due to thermal vibrations and thermal energy, and the electric field sweeps out from the region. That is the way the charge carriers are influenced. There is something known as a pool Freckle ionization, and this you need to study it yourself. It is not very important from the point of view of cryogenic, but I will give you a basic idea here. So if you look at the left hand side figure, it is basically a charge is trapped inside a localized charge trapping. So this is my charge, right, this might be electron in a hole, and it is charged, it is trapped in a trap. So trap has got a negative energy, and negative energy is a stable energy, so all electrons are trapped here. What happens is, because of thermal fluctuations or otherwise, on one side the energy of the barrier actually falls down, and therefore there is a finite probability that the trapped charge carriers need not cover the whole trap. It is something like this, right. Then suddenly what happens is that on the one side of it, it suddenly comes like this. So you do have a probability that the electrons can come out easily from these traps very easily. I will not go into detail of this at this stage, but this is what is known as a pool Freckle ionization, right, and this happens primarily. So the change in the jumping potential is delta epsilon I, right. So your original was epsilon I, now the new value is delta epsilon I, and therefore I can write down epsilon I to be equals to epsilon I prime plus delta epsilon, correct, fine. And this is what is known also as a electric field dependent charge ionization, and also referred to as a pool and Freckle ionization. So what I have effectively done is I have effectively reduced the barrier potential, right. So the barrier potential was very high in one case, now it has reduced to almost half of it, and therefore the probability for the electron to escape the barrier almost doubles itself, right, and therefore you will have large amount of electrons available to you. This is known as a pool Freckle ionization. Now if I do a pool Freckle dwell time versus temperature, it is almost the same as we have discussed till now, but let's look at the fact of what we are trying to do. So this is basically a boron doped silicon with p-type material with and there is an external electric field available to you, which is a parameter. I am varying the electric field and I am plotting the dwell time of a pool Freckle. So it is basically a pool Freckle ionization, and I am plotting the dwell time of a pool Freckle with respect to temperature. As we can see, as the temperature increases, obviously the dwell time reduces, which is as per our understanding till now, right. But let us see what happens when we make the electric field go from a low value to a high value. This electric field is a lateral electric field which you see. When the electric field is low, so let's just plot a graph and show it to you. Maybe let me to get 10 Kelvin, let me draw a straight line here, right. So I have this point, and then this point. You see, for the same value of temperature, as the electric field increases, the dwell time actually reduces, right. And this is what we discussed just now, just before slide, when we are discussing the pool Fresnel ionization, that because the electric field is larger, the dwell time is lower now. Why? Because obviously, because electric field is larger primarily means that the probability that the electron or hole which is residing in the traps, localized traps, energy traps, can easily go away from it and go into the free space, and that is the reason the dwell time actually reduces. So, two things: at constant electric field, the dwell time reduces at fixed temperature, and as the temperature goes on increasing, obviously the dwell time goes on increasing. That is what you have. So, it is basically a hyperbolic curve which you see here. Similarly, at 10 Kelvin, if you look at 3300 volts per centimeter electric field, you see the dwell time is almost 10 to the power minus 10, it has come, right, almost like a 40 Kelvin behavior, right, and that is quite critical. Why it is critical? Because when we do a cryogenic, especially when we do readout circuitry, the bias to the particular device will determine how much amount of electric field is there within a device, and higher the bias of the device, higher will be the electric field, which means the average dwell time will actually go on reducing as you want to generate a larger current in a device, right, and that is sort of a good amount of manipulation which you need to do in order to generate this particular point. Now, so the same graph has again been repeated, but now for a fixed electric field I am varying the temperature, again the same concept, that we have plotted the dwell time here versus electric field, average electric field, for varying values of temperature. As of course, as the temperature goes on increasing, your dwell time should reduce, and that is what is happening. You see, for a fixed value of electric field, the lower is the value of your T equals to 40 Kelvin, lower dwell time is as compared to 4.2 Kelvin, right. So for all practical purposes in cryogenic 4.2 or below, please consider the whole device to be as a frozen device with no option of any generation of charge carriers because of that. Let me come to impact ionization and its effect on the threshold voltage, and we will look into the IV characteristics of cryogenic devices. Now, let's go one by one and we can understand what is impact ionization. See, when the electrons travel at a very fast pace, they gain energy, right, and when they gain energy and when they strike or when they move across the silicon space, they generate electron hole pairs, right, and this is basically known as impact ionization. Because of a strong electric field, the electrons get accelerated, gains energy as half mv square kinetic energy, strikes atom, gives its energy, generates an electron and hole pair. Because of a large electric field, a chunk of electron suddenly appears to a larger extent, and this is known as charge carrier multiplication, and due to impact ionization. There is a multiplication of charge because of impact. Impact ionization, as the name suggests, it impacts with a strong force and electrons get dissipated across this. Now, the charge multiplication can only occur when the applied electric field exceeds the critical electric field required for impact ionization. So, there is a critical electric field above which you will actually expect to see charge multiplication. Any electric field below that, you will not be able to see any charge multiplication, right, or impact ionization. So, two things are important for impact ionization. One is the presence of the charge, of course, there has to be free charge carriers available, the carrier freeze out should not occur, and you should ensure that the electric field within the device is more than the critical electric field available to us. These two conditions have to be met. Look this impact ionization in consonance with the previous discussion, that you require free charge carriers, but at 4.2 Kelvin your dwell times are so large that effectively the charge carriers are frozen, freeze out has occurred, and the number of carriers available for impact ionization is very, very small. So, therefore, the charge multiplication will also be very, very small, correct, and that is what is shown on the left hand side. So, you see you have a critical electric field and this is the x direction, as it starts to go above the actual field, electron hole pairs get generated, and therefore, there is a surge of electrons suddenly moving towards the drain side. Obviously, as I discussed with you, for low technology devices or low technology node devices where the channel lengths are small, the CM is significant because the lengths are so small that the electric fields becomes very, very large. When the electric fields becomes very, very large, there is a large amount of internal multiplication of charge carriers, because of which happens. And therefore, as you reduce the dimension of the device, there is an enhancement in the internal electric field, because of which there is a higher current density that results in larger charge multiplication, right. And therefore, if you remember f theta, you will have also a significant substrate current generation, right. So, not only you will have a large amount of charge carrier generation in the inversion and in the depletion region near the drain end, you will also have a significant substrate current generation which will happen. And so, you might therefore have a leakage current available to you because of this charge carrier generation. So, the potential device issues which you will face are primarily because of the carrier multiplication is latch up, and latch up is primarily phenomena where there is a huge number of carriers suddenly flare up. The currents become so large that because of that there is something known as a breakdown, and therefore the device functioning does not take place. Similarly, there is also a change in the threshold voltage, right, and that is quite critical when you work with submicron devices, especially in cryogenic temperatures. You also have the problem of hot carrier degradation effects, right. Now, let us come to the impact ionization and let us delve into that in detail. On the, if you see the plot at the bottom side, then this is the inverse of electric field, which means that as you move this side, the electric field is actually reducing, right, it is reducing, and I am plotting the value of alpha, which is an in fact impact ionization factor on the x axis. Higher the value, more is the amount of charge carriers or electron hole pairs generated because of impact ionization. And as you can see that this side therefore is basically my E max, maximum electric field, and this is the point where you have E min, where the minimum electric field are available to us, right. Now, at maximum electric field, of course, the impact ionization will be maximum, and therefore you see the values are relatively very large in this case, whereas when the electric field becomes very small, the alpha value goes down. What is to be kept in mind is that even at low values of electric field, for small temperature, the alpha values is relatively large. So, alpha at T equals to 100 Kelvin is much larger as compared to that at 300 Kelvin, right. And this is because of the fact that the relative change in the value of the electron hole pair is much larger at lower temperature. So, you need to keep in mind two important facts in this case, that if you look, alpha is directly proportional to electric field which you apply, and higher the value, more will be the value of alpha which you will see in this case. The equation here which is shown here is basically an empirical expression which takes care of the variation of alpha with the electric field and so on and so forth. These are all empirical in nature, right. Then we plot alpha versus temperature, right, which is impact ionization factor with respect to temperature. As you can see, for lower values of temperature, the impact ionization rate is almost constant, it does not change. But as you move to higher temperature, the alpha value starts to fall down, and this we have discussed in the previous case. Further, as the electric field also increases, see, for a fixed value of temperature, as the electric field increases, the impact ionization factor also becomes larger and larger. This is referred to as a Sutherland model in impact ionization, right. Okay. So, let us now overall see the complete effect of this phenomena, and the first phenomena is basically your band gap widening, the second is basically lowering of the intrinsic carrier concentration, also referred to as freeze out. There is an increase in the bulk potential, incomplete ionization, and there is an impact ionization, right. So, these 5 factors primarily influence the overall characteristics of the device. Just to end up the talk, 3 important slides. The first slide is primarily to look into the shift of the threshold voltage. Please understand that we are plotting here temperature in Kelvin versus the change in the threshold voltage. Change means Vt, the change when I say, I mean to say Vt, which is Vt at a particular temperature, say X, minus Vt at 300 Kelvin. Right. So, obviously at 300 Kelvin everything will merge and this will be approximately equals to 0 because they are equal, right. Whereas, if you go on reducing the temperature, there is a change in the Vt, delta Vt goes on rising and becomes maximum at 100 nanometer channel width, right. It becomes very large in that channel width and it increases drastically in that case, and therefore low width devices showcase a larger change in the threshold voltage. Let us look at the IV characteristics at cryogenic temperature. As I had discussed earlier, you will see that at lower temperature, the currents are relatively very small. You see about 4 to 5 order difference in current is taking place for the same value of gate to bulk potential when you apply the drain voltage, and this is because there is a change in the mobility. Threshold voltage becomes higher on current, and there is a low value of the off current which is visible to you, right. These all results in the lower value of IV. Let me finally come to the cryogenic computing idea. Obviously, it's beneficial. That's the reason we are moving forward with such type of study. We are looking into basically cryogenic modules. There's an improved clock frequency. Per unit watt, the performance is much better when you work at cryogenics. However, there are tacit challenges which you need to face, because at cryogenics the material properties changes drastically in terms of reliability of the material, of the metal interconnects also major takes a role, and therefore even with improved or substantial changes in the device structure, there are certain challenges which are there. But since its requirement is so stringent in quantum computing, that's the reason we study this course. So let me finish this lecture by saying that we have learned today the basic idea about impact ionization, threshold voltage change, current change, and the 5 phenomena which are responsible at the cryogenic device level. With this, let me stop at this stage. Hope you enjoyed the lecture. We will meet in the next lecture again. Thank you.